Am I audible?
Yes, sir.
Okay, the audio quality is okay, right?
Yes, sir. It's quite clear.
Okay. Okay, we'll start in like 2 minutes. So I have added these slides in a location that all of you can access. So maybe later on you can.
So could you paste the link in the chat?
Yeah. So this is so this is the link. You have to replace n with 1, 2, 3, 4, 5, 6, 7. Okay, so currently we are in the middle of lecture 3. Okay, so what we'll do is I'll quickly recap where we are and continue from there. So we were doing this hard margin case, right? So hard margin formulation, what we were doing was we were trying to maximize the margin, right? So the distance we define, the margin we define to be the distance of the closest point from the boundary, right? So that is what we call the margin. And as the boundary changes, the margin is going to change. And what we said was the best classifier is one whose margin is the maximum, right? So
one question.
Yeah.
So we have margin on two sides, right? Both the margin on the negative and positive side, are they equal?
Yeah, that's a good question. So they have to be equal, right? So to see why, see, we are trying to maximize the margin, right? So if I go too close to one particular class, that distance will become the margin, right? So what I'll do is I'll try to move away from, say, for example, there was one image right here. So see here, this distance is the margin. So in my attempt to maximize this, what I'll do is I will try to move away from this particular point, which will take me very close to this point, right? So again, I'll try to move back. So if you remember, if you recall in the last session, we said that it'll, one way to think about it is it'll oscillate and end up somewhere in the middle of these two regions, right? So the margin will be close at the same, rather the margin will be the same on both the sides, right? So that is the image that we saw somewhere here, right? So this entire distance is 2 by norm w. On either side it is 1 by norm w, and this 1 by norm w is the margin.
So like width is equal to twice of margin.
The width is equal to twice of margin. See, this, there is a small confusion there. Some in our lecture, in our course lectures, we have said that this thing is the margin. Okay, but traditionally margin is defined as the distance of your boundary from the closest point. So if you take that definition to be correct, the correct one, then the width of this region, right? This width of this region between the two classes is 2 times the margin,
which is equal to 2 by
norm w. In the exam, you can, I mean, if such a question is asked, right, what is the margin, you can stick to 2 by norm w. Even if you write 1 by norm w, it's okay, we'll award marks for that. Okay, so yeah, I hope you all recollect what we did the other day, right? So we are trying to maximize the margin, And in hard margin SVM, the assumption is that the data points are linearly separable. So we are making hard decisions. And yeah, so this was one error that I corrected. So we now have n data points and m features. So this is consistent with the notation that we have been following throughout the course. So in the exam, in the OPP also, we'll stick to this notation. Okay. So in the OPP, mostly it will be specified. But if it is not specified, then this n will be for the number of samples and m will be for the number of features. Okay, so that is one thing. So each feature vector therefore is in RM, and this is the labels are -1 1 and the data set is given like this. Okay, so we said that the distance of the boundary from the distance of the ith point from the boundary is this value. Okay, evaluate the W transpose X plus B at Xi, divide by norm W. So one trick is if you multiply by Yi, you can get the distance, actual distance. So that is what we have here. The margin is nothing but this. We have to minimize this over all the distances, which is same as this. So assume that that point which is closest to the boundary is Xj, then the margin will become this particular value. Now, since there are several values of W and B which correspond to the same decision boundary, we are going to choose a particular W comma B, right? The numerator of this expression will then be 1. So the margin will become 1 by norm W. Okay, so margin of the boundary 1 by norm W. This is what you have to remember. If the closest point has this particular value, right? If it follows this particular equation, then for every other point, this inequality should hold, right? All of them should be beyond the margin. So they should be greater than or equal to 1. Okay, so this is the constraint. This is the objective function. If you put them together, you get the formulation of the optimization problem. Maximize the margin subject to these constraints. So this constraint, I hope you all understand. All the points should stay outside those two bounding planes. That is what this constraint corresponds to. So maximizing that is same as minimizing the squared norm of W. And this is for mathematical convenience. This is a nice convex function which you can differentiate. Okay, so this is where we stopped. So shall we continue from here? Any questions so far?
Sir, so this Xi, W transpose Xi, which you are seeing here,
yeah,
this is actually one instance of the feature, ith instance of the features, right?
No, this is the ith training example, right? So
ith training example.
right. Yeah,
means it's a row. It's actually a row.
Yeah. In your feature matrix, it's one row, ith row. Okay, so this is the ith row. If you want to express this in Numpy, what you would do is you would do something like this, right? So you would do y. Let me take this one. So you would do if the labels are y, right? And y is n cross, meaning it's a vector of size n, and x is what? X will be of size n cross m, right? So then the constraint, I would express the constraint as sorry, this keeps coming in between, y into, can someone tell me how I would express the constraint? So W is what? W will be
the
weight vector will be of size m, right? It will be number of features, that will be your weight. So how will I express this particular constraint in Numpy?
Bracket weight vector dot t.
Okay.
X at the rate W, right?
X. Yes.
Okay, X at the rate W. And my B is just
take the transpose of X.
So for a matrix, for a feature matrix, it's XW, right? If X is a
Yes,
N.
yes, yes. This is for yes, yes.
Right? So this is just a real number. This is just a float. Right? So I'll express this as xw plus b greater than or equal to 1. Right? I will look for, if I want to look at how many are classified correctly, then okay, let's not go there. But this constraint I'll express like this. Right? I hope all of you got this. We'll try to do some numpy also in between. Is this clear to everyone?
So this equation basically tells that all the points, this is where all the points are.
This particular constraint is telling your optimization problem that make sure that all the points are on to the right of this bounding plane or to the left of this bounding plane. Nothing should be in this width, this region, right? So that's what this constraint is telling you. Make sure that nothing falls inside this region.
So I don't understand, like, because WTX plus B is equal to 1. Like if you see on the right side, that's the equation. And if we see greater than 1, then that means to the right of this dotted line. So that means all the red points, right?
Yeah. So that is for y1, y equal to plus 1. For y equal to minus 1, likewise, you will have those points, you'll have W transpose X plus B equal less than minus 1, right?
So here we can write like constraint of yi belongs to -1 or 1.
That is not needed, right? That is kind of implicit. So that is not a constraint per se. That is a feature of your. See, it's like we don't say that W belongs to R, right? Rn. It's kind of understood. So likewise, yi belongs to -1, 1 is understood. Okay, so any more questions regarding the formulation of the hard margin case?
So could you again show that code to me, sir? I got a little distracted there.
Okay, see, I'm basically trying to express these n constraints in the form of a single numpy expression, right? So this is better if it is done. So, sorry. So my y label vector, right? Label vector is going to be of size n, right? There are n data points. And if there are m features, my data matrix or feature matrix is going to be of size n cross m. And my weight vector is going to be of size m, as many values as there are features. And b is a real number. So what we are trying to do is we are trying to do W transpose X plus B for every sample. We can just express that as XW plus B.
Yeah, I got it now, sir. And this is for each example, and that's the reason you don't take y at, it is just y multiplied by. So yi is -1 or 1.
Yeah. So this will be an element-wise multiplication in NumPy.
Okay, so yeah, got it. Thank you.
Yeah. So now, once this formulation is clear, what we'll do is I will move this here, and I'll move this here. So we are now going to very quickly do a recap of optimization. The reason being, we are trying to minimize some function subject to some constraints. So this is the classic case of constrained optimization, right? So we'll very briefly look at what it means. I think we have all done this in MLF. MLF is a long time back. So okay, so assume that you have a function like this. Okay, it's very similar to the function that we want to minimize, which is norm W square. Right? Norm W is what? Root of W1 square plus W2 square and so on. So norm W square will be something like this, W1 square plus W2 square, which is what we want to minimize. Okay, and we have one inequality constraint there, rather n inequality constraints. Just to simplify things, I'm assuming that we have one inequality constraint. Okay, so I hope you all can visualize this graph here. This is a 3D graph. It's like a bowl.
So what is this equation for?
So this equation is f of x equal to x1 square plus x2 square. That is the function we want to minimize.
Okay, so it's like data, like we have.
It is like this, right? So the reason we are studying this is I want to minimize this function subject to some constraints. So I want to motivate how you do that, or how you go about solving that. So as an example, I have taken something like this. Right, this is very similar in form to this, right? This is w1 square plus w2 square by 2. There are only two weight vectors. I mean, two components for the weight vector. Okay, something like this is what you have here, and you have one constraint. There in the actual problem, you have n constraints. Just to simplify things, I have one constraint here. Okay, can someone tell me what this constraint is going to look like?
It will be a circle, sir.
Yeah, so this will be a circular disk with all the feasible points, right? Being inside the circle. Okay, so the circle, what is the center of this circle?
5,7.
Sorry?
5,7.
Yeah, 5,7, right? So the center of the circle is 5,7. And what will be the radius?
5. Root 5.
Root 5, right? So this is a circle with center at 5,7 and radius root 5. And all these points which could potentially be the minimum are going to lie within this circle because you have less than or equal to 5. Okay, so that is what I have drawn here. This small circle is the constraint, and this bowl shaped thing is your function, right? So you have to look at those values of the function which lie within the circle, right? And among those values, you have to find what is the smallest one, and that will be your minimum. Okay, so this is the setup that we have with this. Okay, if you just take the general form, this is nothing but you are minimizing some f, which is this subject to some g less than or equal to 0, right? Look at this f of x. This is g of x less than or equal to 0. So can someone tell me how I'll write this as in that form, g of x less than or equal to 0?
Bring 5 the other side.
Yeah, bring 5 the other side, right? So that is how you do that. So this is your set. This will be the setup for the next 10-15 minutes. Okay. Okay. Now we have two types of constraints. I'll not tell you what it means now, but we'll just study one type of constraint, which is this case. Okay, so g of x less than or equal to 0, as I said, any solution, right? Any optimal solution is it has to lie within this disk or on the disk, right?
But so don't we have a greater than or equal to constraint? In our case, in the SVM case?
True. So what we'll do is good question. What we'll do is we'll convert that into a less than or equal to. We'll just multiply by -1 and that's a good point. But yeah, this is the form we'll convert that into.
Okay, sir.
Okay, so any solution, you all remember what is feasible point, right? For an optimization problem.
It has to lie within, it has to satisfy the constraint.
Right. Sure. Yeah. So that is the feasible point, right? So anything which satisfies the constraint is feasible for the problem, and all the points within the disk are feasible. Okay. So can someone tell me what this circle is?
That is the function. X1 square plus x2 square.
Contour of the.
Yeah, that is the contour of the function, right? Exactly. So do you all recollect this? I think you did in week 2 of MLF. Do you all know what a contour is?
3D projected onto 2D, right, effectively.
Yeah. I hope you are all on, others are also familiar with this. So I'm moving forward. So if you cut this particular function at the value z, okay, assume that this vertical axis is z. If I cut this function at z equal to 1, then what does it mean? It means x1 square plus x2 square equal to 1, right? So I'll end up with the circle like this. So every point on this circle, right, has the value of f equal to 1. Okay, so now if I want to minimize this function, right? So what should I do next? I mean, any guesses are fine, but what do you think I'll do now?
Take the derivative of
Okay, but this is kind of constrained, right? So yeah, gradient I will take it, but how do I know that it's
Lagrange multiplier.
right? Yeah, yeah. Before going there, so assume that we don't know KKT, Lagrange, and all that. Assume that we are not familiar with any of those things. I want you to think from first principles. I need to find the minimum inside this bowl, right? Inside this disk of this function. So, and I also give you this data that all the points in this on the circle have the function's value as 1. So what will I do next if I want to find the minimum of f?
Sir, I will have to find the distance from this circle to the g of x circle, so that the distance can be minimum. Like, I cannot reach there, but I can go as much close as I can.
Okay, right. So that is what I want to do, right? I see. Somehow I want this disk. Somehow I want this circle to lie inside this disk, right? Otherwise, there is no point, because see here the function's value is 1, but none of these points are feasible. Okay, so what I'll do is I'll make one more step and see if I can get this function within this disk, right? So let me try one more value. Now the function's value is 2.3, and all the points on this circle have the value 2.3.
So I have one doubt.
Yeah.
Like, why can't we take derivative? Like, why do we need constraints to?
Because we have a constraint, right? So I'm asking you to find the minimum of this function subject to some constraint. So I can take the gradient. If I take the gradient of f and set it to 0, I'll get 0, 0, right? That's where the function is minimum. But 0, 0 does not lie inside this disk, right? So that is not, according to my problem, that's not even a feasible point.
If we don't take the constraints, the plane would just go to -infinity if it has to minimize.
Right.
So we have to take it.
Okay. So now, can you tell me if any point on this circle, f of x equal to 2.3, this contour, any point on this contour which intersects this disk, can it be the minimum?
No, it has to be tangent.
Why should it be tangent?
Because you can always find a point which has a lower loss value. If it is intersects, then you can always find another point where the loss value will be less.
Okay, so high, right? So see, we are trying to minimize f. So if you try to go beyond this tangent, right, beyond f of x equal to 2, you will end up with feasible solutions like this. But for those feasible solutions, f of x will be higher, right? But we are trying to minimize f. Did everyone get this point? Because this is like, if you want to like appreciate the rest of the slides, it's important.
Yeah.
Okay, right. So recall, I mean, in case you are not getting it properly, notice that as I go away from the center, my function's value is getting bigger and bigger, right? This is like a bowl. And as you move away from the center of the bowl, your function is going to, the height of the bowl in some sense is going to be bigger and bigger, right? So you want to stop at just that point where I just satisfy the constraint, which is f of x equal to 2, right? This is that point where I just satisfy the constraint, and that will also be optimal.
Then I remember in MLF, the prof gave an example of a cow tied to a pole with a rope.
Ah, right, yeah.
So
The coordinate was 30, 40.
Yeah.
Right, that was one example, right? So I am assuming that we can move forward, right? So now the contours of f, right? This contour is going to be tangent to this particular constraint, and this particular point, right? That is going to be the optimal point. Okay, so this is what the gradient of f, right? So can someone tell me why the gradient of f is pointing in this direction?
Because the function has steepest ascent in that direction.
Correct, right? So the function has steepest ascent in this direction. This is the direction in which the function is increasing the maximum. Okay, and it is also perpendicular to the tangent at this point, right? So this is the direction of the function. What do you think will be the direction of the grade of the constraint here? If g of x is the constraint, what will be its direction? The gradient of g.
I think minus of g dash x.
See, gradient of g is the gradient, right? So del g, I'm asking.
Opposite to del f?
Sorry?
Opposite to del f?
Right, you are right. So why is it opposite to del f? Okay, so if del f is in this direction, why is that? Because this is the direction in which f is increasing the maximum, right? You are moving away from the bowl, so del f has to be in this direction. What about g?
So in G as well, where the function is increasing as well. So I think because it's a bowl shape, right?
Okay, yeah. So
are we saying that delta F is increasing the most when delta is?
Okay, yeah. So the way to understand for g is that within the disk, right? G is decreasing, right? If you just step back into this disk, g is decreasing. So it is natural that the gradient of g should be in the opposite direction, right? So that is where g will the function g will increase, right? So g should be in this direction. Okay, so from this what we get is the gradient of f is in the opposite direction of the gradient of g for some lambda, right? Lambda is will be some positive value. They don't need to be having the same value. So this vector is anti-parallel, as we say, right? Is parallel to g but in the opposite direction. So we get this. If you rearrange, we get something like this. Okay, so is this familiar to all of you?
Yes.
Yeah.
Okay, right. So this is gradient of the Lagrange, right? So I'm just going to take the gradient outside. This f of x plus lambda g of x will be what? It will be the Lagrangian. Okay, so this is a very brief motivation of how we get hold of this Lagrangian in the first place. So recall that this lambda should be positive, and at this point g of x is equal to 0. Okay, so this is why these three things put together make this constraint active. So when I say active, it means that you can't just you can't just do gradient of f equal to 0 and find the minimum. The constraint is going to tell you that that is not the actual minimum. right? So you have to take into account the constraint. So that is why it's called an active constraint.
So I didn't understand this.
Okay, see, there are two problems. Assume that there are two problems. One is an unconstrained problem. So the unconstrained problem is that minimize, say, W1 square plus W2 square. Okay. Now, say there's a constrained version of this problem which says that, so the objective is the same. You want to still minimize W1 square plus W2 square, but subject to some constraint. What could be the constraints? Let's say 2W1 plus 3W2 greater than or equal to 0. Say something like this, or less than or equal to 0. Okay, so these are two problems. Now, I call this particular constraint active when, having this constraint forces the minimum to be different from this unconstrained problem. Do you get it? So see, how will you find the constraint? How will you find the optimum value for this unconstrained problem?
Just take derivative.
Yeah, just take gradient equal and set it to 0. You will get 1 point, right? So in this case, it will be 0, 0. Right? Now, if your constraint, if you try to solve this, right, and if 0, 0 is still the solution of this constraint problem also, then this particular constraint had no use, right? That case is called inactive constraint, where it's as good as not having your constraint at all. But if introducing this constraint, makes your optimum something like, say, 1, 2, right? Then in that case, your constraint is actually becoming active. It's making sure that that it matters. That is what I am trying to say here, right? So here this g of x, by being equal to 0, make sure that del f equal to 0 doesn't give you the actual optimum. Okay, I mean, if even if you don't understand, or if I haven't explained it properly, don't worry too much. Like, it's not too important, but it's good to know that the optimum in this case is not the same as the optimum of the unconstrained problem. That much you understood, right?
Yes, sir.
Okay.
But if gx is less than equal to 0, that is the constraint, then why are we writing just equal to 0?
No. So this is just one case, right? So this is one case where the constraint, as I said, becomes active, right? So
Taking one constraint at a time.
no, in this case, this is the only constraint, but this is one scenario where the constraint becomes active. I'll also show you another scenario where the constraint is inactive, right? We'll come to that. So this is the second part, right? Consider this constraint where something like this is happening. Okay, so in this case, what will happen is, if I set the gradient of f equal to 0, right, that will give me the solution to the whole problem. So whether this g of x less than or equal to this there or not, I don't care. Yeah, did you get that part, all of you?
So here our constraint and our function completely overlap.
Yeah. So having this constraint is like not really changing my optimum of the unconstrained problem in some sense, right?
So actually, our optimum lies inside that feasible region.
Correct. It already, the optimum of the unconstrained problem 0, 0 already lies inside the feasible region. So in that case, we call this constraint inactive. Okay, so what we'll do is, here also we'll come up with the Lagrangian, but there is one thing that we'll add here. If we have this condition, then what can we say about lambda for an inactive constraint?
0.
0.
right? Lambda has to be 0.
Yeah.
Right, and g of x is less than 0 in this case, as we can see. It's inside the feasible region. So this is an inactive constraint. Now, if we see both of them side by side, you will understand. When g of x is equal to 0, lambda is greater than 0. It's an active constraint. When g of x is less than 0, right, lambda equal to 0, and this is an inactive constraint. Okay, so if we plug these two together, can we come up with one more condition? If you use these 4 snippets of information, can you condense them into one single condition?
Lambda is greater than equal to 0 and g of x is less than
Right. In a single expression, can you tell me? Can you put? Combine both of them.
Can we do this just putting minus?
Okay.
It would be like lambda is greater than equal to 0.
Oh, lambda g of x is greater than is equal to 0.
Exactly. Right. So that is what we can conclude. See, in every case, one of them is 0, right? Either lambda is 0 or g of x is 0. So if you multiply the two, whether the constraint is active or inactive, we know that lambda into g of x is equal to 0. Okay, so all that we have done so far is formulate these 4 conditions for an unconstrained optimization problem. So first we came up with what is called the Lagrangian. We saw that gradient of f and gradient of g should be anti-parallel. Therefore, we want lambda to be positive, right? So that is condition 3. Condition 2 comes from the optimization problem itself, right? This is the constraint. Condition 1 we just saw, right? So that is what we started off with. And the final condition we just saw previously, right? So these are your necessary conditions for that an optimal solution should satisfy. Okay, so this is a quick recap. Do you want to spend more time on this, or I can move on to the next slide?
So I think it was covered in MLF, like primal feasibility, dual feasibility, slackness, and all that.
Yeah, so that is just a quick recap. So we can move on then.
So I've just small doubt, like.
Yeah.
So like in the previous slide, like where you have graph. Previous slide, like
graph, right?
Yeah, like where you drew direction like of delta f and delta g.
Yeah.
So here, like I didn't understand why we're calling that delta f and that delta g, and why are they anti-parallel here? Like I don't understand.
See, there are 2 things here you need to know. One is the gradient of a function is always perpendicular or normal to its contour, right? That is fact number 1. Fact number 2 is that the gradient of a function always points in the direction of greatest increase of the function. So these are 2 points. Now if you apply them for these 2 functions f and g, you will get these directions. In this direction, g is decreasing, therefore del g should be in the opposite direction. And for f, because of the bowl shape, f is increasing outward, so it has to be in this direction.
So like f is also increasing in other side as well, because it's a bowl, so it's increasing in both sides, not just one side.
It's a bowl, right? So if you it is increasing in, I mean, the maximum increase is only in this direction. I mean, it can increase in some direction like this, right? But that is not the steepest ascent.
And what about like just the opposite of delta f, that direction?
That will be a direction of steepest descent, right? That is the whole basis of gradient descent. You choose a direction where the function decreases the most. That's why we do w equal to w minus learning rate into gradient of f, right? So that is the reason we choose the opposite direction.
Sir, I think she's talking about the third quadrant, sir.
Third quadrant.
Like what will happen to the gradient in the third quadrant?
Everywhere on the circle, it will be normal to it, outward.
Normal to it. So in the third quadrant, the del of f will be outside, no?
Yeah, everywhere. So this will be like pointing outside the circle for all the points.
Yes, sir. Yes, sir.
Right. So yeah, again, as I said, this is just a quick recap. It's okay if you don't quick like follow it that well. Right. So I will move these away. Now, why is all this relevant? Because this is our constraint optimization problem for hard margin case. Right. So not the thing that I have done here. I have just changed the sign so that this becomes g of x less than or equal to 0. Okay, so minimize f of x subject to g of x less than or equal to 0. There are n such constraints, one for every training example. Okay, so we'll go step by step. Remember that the first step we have to do is come up with the Lagrangian, right? So is this step clear to everyone?
Yes, sir.
I have added n Lagrangian, n multipliers, n lambda 1 to lambda n, one for each data point, and this thing is the constraint, g of x less than or equal to 0. That constraint goes here. Next step is to compute the gradient of L, right, with respect to W.
So we are finding minimum of W and B in one shot, is it? In one Lagrangian. That's how it works. Is that?
Yeah. So this is, so it's like you can treat W comma B as one bigger vector.
Okay.
Right. So.
But when we find the gradient, you're doing it individually for W.
Yeah, we are doing it individually. Okay, right. So this is first step is we'll take gradient of L with respect to B. Do you want me to explain this? This is quite simple. This norm W square is nothing but norm W square is nothing but W transpose W, right? And if you take the gradient of that particular expression, I'm calling it f of W, you will get 2 into W. Okay, I hope this is clear to all of you. So that is how I get this W expression here. The second part is quite simple. This is just minus yi W transpose xi, right? So if we differentiate it with respect to W, I just get minus yi xi. Okay, and the lambda is anyway there. So that is how I differentiate with respect to W, and this has to be 0. So this gives us a simple expression for W as summation over all these n data points. You weight the feature vector by its label and some Lagrange multiplier lambda I. Okay, this is step number 2. Now you do the same thing for B, right? So if you do it for B, what will happen is this will vanish, lambda i's will vanish. This doesn't depend on B. So the only thing that depends on B is this one. So this will be sigma lambda I yi, right? With a minus sign. Sigma lambda I yi with the minus sign. And this is the gradient with respect to B. Okay, any doubts so far? Okay, so what happens next is we are going to eliminate W and B from the Lagrangian. Okay, so what we'll do is we'll plug back W and B into this particular expression. So that is what this will be, a slightly longish step. Okay, so first thing that I'm doing is I'm focused on this sum. We are like writing this down as 3 sums, right? So sigma lambda I W transpose xi, and something like this, right? There are 3 terms here, and we are just expressing it as 3 sums. Okay, so can someone tell me what will happen to this expression on the rightmost expression?
0.
That will become 0. Does everyone see this?
So the last condition.
Yeah, so the last condition kicks in, so this term becomes 0. Okay, so that vanishes. Okay, so this is simple enough, so we are leaving this as it is. We'll take up this particular fellow, right? So notice what is happening here. Can someone tell me how this expression came about? I put it down there, but just want to know if you all understood this.
Sir, you have taken the constant term outside.
Yeah, so what is the constant term here?
W transpose.
Right, so I have just taken this W transpose out. So this expression is what?
W.
Okay, right, so that expression is W. As we can see here, when we try to find the gradient of L with respect to W, this is what W turned out to be. So this is nothing but norm of W square. This whole thing is norm of W square. So what will this expression become now? We have one norm of W square by 2, and this is minus norm of W square.
So
sigma lambda I minus norm of W square by 2.
Correct, right? So sigma lambda I minus norm of W square by 2. So all that remains.
How that lambda I ya equal to 0? The last condition.
Okay, so that comes from differentiating L with respect to B. You will see that sigma lambda I ya is equal to 0. This is coming from differentiating with respect to B.
And equating to 0?
Yeah, and equating to 0.
Like why we are equating to 0?
That is
the minimum?
That is the first step in our KKT, right? So if you formulate the Lagrangian, then the gradient of the Lagrangian should be 0 with respect to the variables.
Okay. Like, but W we are not equating to 0, right?
Yeah, W we did, right? So W we did. So that is how we got.
Okay.
Yeah, so these two are with actually the result of gradient of L with respect to W equal to 0. This is for B with respect to L with respect to B equal to 0.
Okay, sir.
Okay, so if you plug all these things inside, you end up with this. Okay, now can someone tell me what will be the next step? We have to eliminate W. How do we do that? How can I rewrite norm W square as?
W, you can't write this as
transpose W.
Not lambda I ya xi.
Yeah, so yeah, that's the right direction. So what we will do is we will write W as norm W square as W transpose W, and then plug this W here, right? So that's one big step. I have just collapsed the whole thing here. So W transpose W, and then just substitute these summations here. You end up with this. So does anyone? So please spend some time on this and let me know if you can proceed.
So like lambda and yi is equal to 0, and if you plug in that value, then everything will become 0 here.
Where?
Like lambda I into yi, we have this equation, and if we put it equal to 0, then everything will become 0 like here.
No, right? Because this is lambda I ya xi. You are forgetting the xi that is there. If it is only lambda I ya, then you are right. But this is sigma lambda I ya xi. No.
So where did the half come from?
Half we carry it over from the optimization objective itself. Right? So this half is there all through. So it didn't go anywhere.
So that happens for mathematical convenience, because when you take the gradient, the 2 degree comes in, so it cancels out. So it's
Oh, okay. Sorry. Oh, this half, I think you're asking about this half. Yeah, this is wrong. Sorry. This half should not be there. I kind of added it by mistake. This will be there. This half is not there.
Okay, sir. Yeah, thank you.
Yeah, so that I'll correct it. So this half.
The first step of lambda I y xi, the whole transpose, how did it become just xi transpose?
Okay, so that's like this, right? So if you have, see, you must recollect that these are all vectors, right? So if I have two vectors x1 plus x2 transpose, I'm just writing it as x1 transpose plus x2 transpose. That is what I'm doing here.
Oh, so yi is not, it's just a single dimensional vector.
Yeah. Ya and lambda I are all scalars, right? Ya is the label -1 or 1. Yeah, okay. So that may be confusing. So see, in the whole formulation, W is a vector, Xi is a vector. Everything else is a scalar.
Scalar as in xi is multiple features, therefore you are saying it's a vector, and yi is just one label for a number of features. That's why you're saying it's a vector.
Yeah, see, there are n examples, right? N training examples. And xi is the feature for the ith training example. So it will be some m dimensional vector. And W is anyway m dimensional. Okay, Ya is in -1, 1.
Okay, so for that specific example, lambda I and yi are just one scalars, whereas that xi is a vector, and that's for your transposing that.
Yeah. Right. So W, this whole thing is a summation of several vectors. So basically, it's a sum of, if you want to think about it, it's like you're adding all the training examples together, all the feature vectors together, but you're weighting them by lambda I Ya.
Can this be expressed as a in a vectorized form? That will be, I think, if you are coding this one in Numpy, we'll have to do it in a vectorized form. It's a dot product looks like.
Correct. Yeah. We can do that. So see, this is basically Xi transpose Xj for all Ij, right? So this can be done. So something like, say, if X is your n cross m feature matrix, and I am not sure if X transpose X will do it. I'm not sure, because finally you need what? You need this to be n cross n, right?
It will be m cross m.
N cross n, right? Like this, the outer loop. Outer loop runs from 1 to n, and inner loop runs from 1 to n. So
yeah, n square, yeah.
Right. So this is okay. This is probably x
transpose. Yeah.
Right. So is that correct?
Okay. If you do that, the dimension will be n cross n for this product.
Yeah, dimension will be n cross n. It will also give us what we are looking for, right? So, for example, see, let's take the case of 3 examples, right? So I have say x1. So X will be your feature matrix, right? So each row is a training example. So this is, assume that you have 3 training examples given by x1, x2, x3, right? These are all row vectors. So x1 is like this. So
these are feature vectors transposed.
Yeah, these are all feature vectors transposed. So better to express them as x1 transpose, x2 transpose. So x1, x2, x3 are column vectors, right? So these are all rows of the feature matrix. Now, X transpose will be what? X transpose will be something similar, but this will be x1 x2, x3, right? As columns. So these are all columns. So if I want to do this x into x transpose, what will it be? The first, can someone tell me what the first element of this matrix will be?
X1 transpose X1.
Yeah, it will be x1 transpose x1. What will be the second element?
X1 transpose X2.
X1 transpose x2. And then x1 transpose
X3.
Right. So this is x1 transpose x3, right? So we have one row like this. Now we can also write the other row. It will be, I'll just go ahead and fill it. x2 transpose x2, x2 transpose x3, correct? And this will be what? x3 transpose x1, x3 transpose x2, and x3 transpose x3. Right. So what? Yeah. This. Thanks for pointing this out. So this might add one more dimension to this. So what we are computing here is one element of this matrix XX transpose. And did everyone get this connection? Okay, so at least this part that's what we are computing. XX transpose is the elements of XX transpose is what we are computing here. Okay, so shall I move on now?
Yes, sir.
Okay. All right. So see, finally we end up with an objective function that involves only lambdas. Right? It doesn't involve W and B. So we are initially trying to minimize some expression in W and B. Now we are trying to maximize an expression in the lambdas. So this is what we call the dual form, right? So if you recall from MLF, we end up with the dual form of that primal problem.
So could you just show the primal ones?
Yeah, so this is what we had. The primal is this, okay? So this is in terms of W and B, we are trying to minimize it. What we did was we first formed the Lagrangian. We set the gradient of Lagrangian to 0 for W and B. So that gave us two equations in where W is this and this is something else, right? So what we did was we eliminated W and B from this objective function of the primal, rather this Lagrangian, and we ended up with something that has only the lambdas, the Lagrange multipliers, and this is the dual objective function.
So the primal problem was originally what? It minimize WB, maximize lambda for that. Is it? Is that the primal problem?
So the yeah, see, this is slightly different from what was. I'm expressing this slightly different from what was done in the MLF course. So I am following the Bishop book here, right? So.
So what does that L of WB lambda mean then? What are we doing over lambda?
This is the Lagrangian, right? So you are forming the Lagrangian, and the Lagrangian takes this form.
Okay, but there is no minimization or maximization involved here, is it?
No. So what I am doing here is I am just applying these conditions here. So this is a template. Just think about this as a template for converting this to the dual. So I form the Lagrangian and then I apply these conditions. In some sense, that's what I'm doing. Okay, so if this is vague, I totally understand because it is vague for me also. So
okay, I mean, more than vague, I think it's slightly different to the way at least I've learned in MLF. So that's why I'm just trying to map more than anything else. difference.
Agreed. Yeah, it's kind of different, right? So most, at least the bishop, the standard reference that we are using for this course follows this. So I have stuck to this particular formulation. Okay, so the point to note is that from trying to minimize the objective in terms of weight and bias, we have come to a form where we try to maximize in terms of the Lagrange multipliers lambdas. Okay, there's absolutely no involvement of W and B in this.
Yeah. So one other thing is here, the dimensions are higher compared to the primal form. Typically, people solve the dual problem in a lower dimension. In this case, with actually the dual is in a higher dimension.
Okay. So,
I mean, most of the time when we are formulating objective function, we'll get the same answer whether we solve the primal form or the dual form. And most of the time, it makes sense computationally to solve the dual, provided a dual dimension is less.
Okay.
Yeah, from a computational efficiency standpoint, right? So, but here it looks like it's going into the higher dimension.
Right.
Yeah.
Okay, so if you observe this is what is called a quadratic programming problem. Okay, in fancy terms, but this is quadratic because you have lambda square, right? In some sense, lambda I, lambda j. So the degree is going to be 2. Okay, so the objective function is quadratic in the variable that you're trying to optimize, which is lambda. And your objective functions are all linear. So that is like a typical case of what is called a quadratic programming problem. And we are not going to look into how to solve that, right? All that is going to be a black box for us. Even coming this far was like tricky. So we won't venture into what the whole thing is, but we can rest assured that there are several quadratic programming solvers where if you plug in this matrix, right? So for example, the whole thing can be represented as a matrix. So if you remember the positive, definite, semi-definite weaks in MLF, you can write this expression as say lambda transpose A lambda, where A is this x transpose times something. So do you all see that? So x transpose Ax, do you remember seeing x transpose Ax in MLF?
Yeah, we calculate the polynomial, that quadratic, the polynomial thing from that.
Yeah. So anyway, so that is that same thing here, but we don't need to worry about all that. So only thing that you need to understand is if you plug this into a quadratic programming solver, it will give you the optimal values of lambda. Okay, so now how do you go back from lambda to your weight? Finally, we want weight and bias, right? That's what we are here for. So how do you get the weight and bias? You go back to the initial expression that we had, W equal to this, right? We got this from taking the gradient of the Lagrangian with respect to W. So just plug this optimal value of lambda into this, you get your optimal weight vector. Okay, now final part that we are coming to, why is this called a support vector? It's a long list of things. So first recall that we had this one KKT condition that lambda I should be non-negative, right? They should all be greater than or equal to 0. And we also had another condition, right? This lambda into g of x should be equal to 0. That is this condition. Okay, so when your constraint is active, when g of x is equal to 0, this will be 1 and lambda will be positive. Okay, if the constraint is inactive, can someone tell me what will happen? Lambda will be 0 and this will be greater than 1, right? So so this is very important to understand if you want to know what support vectors are. So if you look at it, typically what will happen is the solver will return the values of lambdas, and for most of them, lambdas will be 0. Okay, so for most of the values, for most of the data points, lambda will be 0. Those points for which lambda is not 0, they are called the support vectors.
So in this case, then W transpose Xi plus B equal to 1, basically.
Yeah, right, exactly.
The condition.
Yeah.
All
So
those points in the boundary.
Yeah, exactly. Right. So this is how the support vector name actually comes, right? So all those points on the boundary, this is why they are called support vectors, because they in some sense support or lend their support to form the weight vector, right? It is because of these non-zero lambdas that you're able to form the weight vector.
So
Okay,
did
so
you understand the last 2 points, sir?
which one?
Sir, lambda I for most of the data points, lambda I equal to 0, and those points lambda I greater than 0 are support vectors.
See, for most of the, this is assume that this is a fact, right? So if you try to solve this, if you send it to a solver, it will return one lambda, right? Now most of those lambdas will be 0. Okay.
For non-support vectors.
Yeah. So assume that we don't know what support vectors are. So I'm just trying to motivate how it got its name. So it's like I'm defining support vectors as those for which the Lagrange multipliers are non-zero. Right. So it's like I am kind of trying to generate
as a convention, sir.
Yeah, you could call it convention, but it's more like how do they arise, right? So see, there is one way to understand it by saying that everything which lies on the bounding planes, right, on these two lines are support vectors, right? But that seems arbitrary, right? So I mean, who told you just come and tell me that if it lies on this line, if a vector lies on this line, it's a support vector, right? So that seems like unfounded, right? So what we have done is we have tried to give a mathematically strong reason for calling them support vectors, right? If you solve the optimization problem, you will get some non-zero lambdas which determine the weight vector and which also happen to lie on these two lines, hence they are called support vectors.
Sir, one another thing, like the conclusion that you draw, lambda I equal to 0 for lambda I greater than 0 for support vectors. Has it got something to do with this constraint being active or inactive?
Kind of, right? Because when the constraint is inactive, that is if your points are like far away from the boundary, for them they don't really influence your optimization problem, right?
Yes, sir. Now I am getting. Yes, sir. Yes,
Okay,
sir.
so that is why they are, for them lambda is 0 because they don't really contribute to your optimization problem.
Yes, sir. They will. They will not contribute to the optimization. Now I understood, sir. Thank you, sir.
Right. So finally, we can express this in this form also. W is summation of lambda I y xi for those xi which are in the set of support vectors. Okay, just a different way of expressing it. Okay, so that is the end of hard margin SVM. So is this picture now clear somewhat what we are doing?
So these support vectors are really vectors orthogonal to that boundary line that goes to these points. Is that how we should think of it? From the boundary that we have in the middle, are these vectors that are orthogonal that touches these points on the boundary? I'm just trying to think why they call it support vectors.
See, they are all vectors, right? At the end of the day, x1 is, okay, they are called vectors just because they are like this, right?
Okay. The data itself is called a vector, therefore.
Yeah. So that is the reason it's a support vector.
And we can draw a Cartesian plane and like represent them as vectors.
Yeah, right. So what is missing probably from this image is the axis, right? So if I had drawn the axis, it would have become clear. So from origin to that point will be a vector.
Yeah. So essentially, it's a subset of the data elements, which essentially define those two boundaries, one on the left, one on the right. The rest of the data elements don't really contribute to the definition of that hyperplane on the either side, and then obviously the main separation is in the middle, right? So
exactly, yeah.
So this is actually, I think, fundamentally different from least square, where every data point contributes. Here, only those 3 blue points and 2 red points contribute to the hyperplane. Rest are basically, in some sense, we can say it is resistant to outliers, right? If on the left or right, deep inside the territory, it doesn't really matter. What matters is the vectors in the boundary, closer to the boundaries.
Yeah, exactly. Yeah. Right. So the other advantage of that is that during inference time, right? So during inference time, you want the sign of this, right? So what you can do is you can throw away all these points and you can only retain the support vectors for inference. Right. So that's like a memory and computation saving, right? So you don't need any of these points because they are not going to help you with the decision boundary, forming the decision boundary. So you just need, okay, you have condensed all your information into just these 5 points here. Okay, so that is the end of hard margin SVM. Now final part is soft margin. So there is actually a problem with that. I'll discuss this, what the problem is. Okay, so did everyone get what happened so far? Or at least like 50% of it?
Yes, sir.
Okay, right. So the tough math part is over. Now it's like.
So in statistics, we learned about sufficient statistics. Can we relate those here?
He may not be the right person. Probably Nitin. I'll ask Nitin to help out.
Okay, thanks.
Right, because Nitin has been an instructor for Stats 2 also, so he'll be able to comment much more than me. Okay, so we now come to the soft margin case where we are still linearly separable. So it's not linearly separable, but still there is some kind of chunking here, right? So I can draw a line technically, but I'll end up making mistakes, but that's fine. Maybe I won't make too many mistakes, right? So I've just called this case nearly linearly separable for that reason, right? So these two red points are going to be wrong. These two blue points are going to be wrong, but predominantly you're going to get things right. Okay, so will my hard margin minimization problem work here?
Not separable. Yeah.
No, right? It won't work because it's a hard margin, right? Your constraints will fail. You will have no feasible solution. Your feasible set itself will be empty, right? Because this case 4 constraints will be violated for these 4 points: red, red, blue, blue. Okay, so clearly that won't work. So to fix that, what we do is we are going to talk about errors, right? Errors in not exactly classification, but we look at what it means. So is this base image clear to all of you? This is W transpose X plus B equal to 0. This is one bounding plane. This is the other bounding plane. And everything to the right of this is greater than 1. Left of this is less than -1. And all points red. I'm only going to talk about red points. So it's all +1 labeled. So is this base image any doubts here, or I'll move on?
No, sir.
Okay, right. So see, what is the error? I mean, I have not told you what the error is, but what do you think is going to be the error of this data point?
It is covered in the video. It is a distance from that bounding plane, like eta I or whatever it is called.
Right, psi I, or let's just call EI. I mean, E for convenience. But what will be the error? Assume that you don't know about that. So what do you think is going to be the error for this point?
1.
How far it is from that bounding plane? Like if we do an orthogonal projection of that point into that bounding plane, that's how far it is off from that.
Okay. So assume that this entire region is it corresponds to red region, right? So this is like the correct region for red
Error will be
points to be.
0, right?
Okay, right. So that's correct. So E1, let's call this E1. I think it's Xi, but it's a bit tough to pronounce. So let's call it E1. So this point does not have any error because it's classified correctly. So error is 0. Okay. So what about this point?
Okay, got it. Zero.
Okay. So E2 is 0. Okay. Now, where do you think I'm going to draw the next point?
On the left side.
Okay. Where exactly on the left side? Any idea?
Sir, it can be between the margin or it can be totally on that side, like in
Okay, right. So I'm going to draw it somewhere between the bounding plane and this margin. So that is E3. So what do you think E3 will be?
E3 will be the distance
0.
between the border and the point.
Okay, so think about this. What is our objective in SVM? Point should lie beyond the margin, right? They should lie beyond this margin. Red point should be on the right side of this margin. So my notion of error is that if it is not on the right side of the margin, I start penalizing that point. So I want to add some penalty to this point. What penalty can I give?
I see. How far it is off from that bounding plane.
Correct, right? How far it is off from this bounding plane. Okay, so say I'm going to give it 0.5, right? So see, there is a way to think about this term, right? W transpose X plus B equal to C, right? This thing has a distance, right? So I'm saying that this bounding plane is 1 unit away from the decision boundary. So this particular point is 0.5 units away from this bounding plane. Is that idea clear?
Yes.
They're all parallel lines, right? So I'm kind of justified in talking about distances between lines. So I'm saying that this point, the third point, is 0.5 units away from where it should have been. Ideally, it should have been on this line or away from that line. But it's like 0.5 lines on the wrong side of the margin. Okay, the next point is going to be this.
Sorry.
Yeah.
Can I just ask a silly question? So this E3 is really is still the training data that we're talking about, or is the test data? Because training data means the boundary would have already been drawn with E3 as the boundary, right?
No, right? So correct, good point. But see, we are now in this soft margin case, right? Where
non-separable.
Yeah, it's not separable, right? So
Solution can't be found as hard margin.
Yeah, it can't be found as hard margin. So there'll be a trade-off. We'll discuss that trade-off very soon between how big your boundary is going to be. And see, now we are going into this domain where my margin is going to be defined by, this margin is still 1 by norm W, but I'm going to just stick to these bounding planes now.
Okay, that norm W, we don't know which point to, or okay, there's some method we're going to figure out.
Yeah. So we'll have to forget for a while this. There is no more this concept of what is the closest point to the bounding plane, because
right.
I might potentially misclassify also.
Okay.
This is probably more real life situation.
Yeah,
because
this is
real life. You don't get a separable case always.
True.
Yeah.
Okay, so what will be this E4?
1.
E4 will be 1, right? Because it's correctly 1 unit away from this. So there are 3 more possible points. Okay, one inside this margin, one on the other side of the margin, and one beyond here. Okay.
2 greater than something 2.
Okay, so this will let's call this E5. E5 is what?
1.5 or whatever.
Okay, E5 will be 1.5. That's right. What about E6?
2.
Okay, that is 2. E7 will be
something greater than 2.
Okay, right. So that is right. So this is 1.5. This is 2. This is 3. Roughly, right? So these are the errors. Okay, for all these 7 points, for first 2 are like fine. We don't penalize them because they are on the right side of the margin. But the remaining 5 points, we are going to penalize them by how far away they are from this particular boundary. Okay, is this image clear to all of you? Okay, I'm assuming it is.
Yes, sir.
Okay, so from this, we get the expression for this error. EI is equal to 0. Xi lies outside the margin. By outside, I mean beyond this correct side of the margin, right? So this is the margin. So I'm using this margin in a different sense now. I'm calling this bounding plane the margin. Okay, so please don't mind that. If it is beyond this bounding plane, then it is 0. If it is on the other side, on the wrong side of the margin, then my error will grow in this fashion. The farther away I am from this unit 1, the more is going to be my error.
But the distance was calculated as WTX plus B by norm of W, right?
Yeah, good point. So so you have to think about this way. What I am doing now is, when I say distance, I am using different units. So you can treat norm W as a unit conversion tool, right? So for example, this bounding plane is actually what? 1 by norm W units away from my decision boundary, right? Is that right? So I am this bounding plane. Let me just write it down. The bounding plane W transpose X plus B equal to 1 is, what is this going to be? This is going to be 1. This is correct, right? This is going to be 1 by norm W units away from my decision boundary. What I'm saying is, let's say this is in, say, centimeters. I am saying that this norm W is a conversion tool from centimeters to meters. So I am equally justified in saying that the bounding plane is 1 unit away from my decision boundary, where the units I use are different. Say here it is centimeter, here it is meter. Okay, I've just changed the way I'm measuring my units.
This is a change in the metric space.
Yeah. So I'm just changing this. Say I probably this is centimeter, and by dividing by or multiplying by norm W, I go into meters.
So it's just starting with 1 unit away.
Correct.
One in the new unit.
Yeah. So the points, the lines that are going to be important for me are going to be 1 unit away from my decision boundary, and that is going to be my zone of confidence in some sense, right? I don't want anything to penetrate that. If some data point is penetrating that region, then I'm going to penalize it, and this is how I'm going to penalize it. In my new units, this is the penalty. 1 is the distance of this point of this plane, and y into W transpose Xi plus B will be its distance from here, right? So 1 minus that will be this part.
So YIWTX plus B will always be a positive number. So can this whole thing become negative?
Good point. So this can never become negative, right? For the following reason. See, so first think about just W transpose Xi plus B, right? This is greater than 0 for all points in this region, right?
Right.
So YA is plus 1, right? So, okay, this is a good question.
We discussed last time also. Once we cross that, YA becomes negative. So negative
cancels.
But the thing is, because it's a red dot, it will still be 1. It will be positive.
And so why are we penalizing those points which are inside the boundary rather than outside?
Yeah. So those are two questions, right? So wait one second. See, YA is plus 1. Okay. So see, the reason we are penalizing points is I want to keep my boundary kind of free of points, right? This is This is coming from the hard margin case where I didn't allow any points to fall within these two bounding planes, right? So I'm going to start penalizing right from here. Ideally, you're right. We should penalize only if it is misclassified. That is, red point falls here. But I want to be more conservative and say that the moment you enter the boundary, enter my margin, my zone of no entry, I'm going to start penalizing you. Okay, so is that point clear?
Yes.
Okay, but sir, again, that would keep changing, right? As we train the model. I mean, the boundary. Yeah.
That will keep changing, right? We'll come to that. There's a trade-off which will become clear.
Okay.
But this question of this is always positive, but just give me 1 minute. I'll.
Sir?
Yeah.
1 minus yi, the expression that you wrote, 1 minus, that can go to negative. The whole expression can go to negative, na?
That should not. Once again, I'll just take up this particular image and see this thing is always +1. Okay, assume that we are now discussing this whole region is great. Yeah, so this whole region is greater than 0. So this region we are talking about is positive. So in fact, we can be a little more precise and say that this will actually be 0 less than. Okay, this is this region, right? Can we all see that?
Yes.
Yes, sir.
Okay, so once again, I'll just delete this. We don't need these things anymore. Epsilons are not needed now. So this region is actually going to be between 0 and 1. Okay, so here, what is that expression? For epsilon I, epsilon 1 minus this, right? Okay, so this is going to be between 0 and 1, right? 1, let me also write that down. 1 minus y into w transpose x plus b. This is that xi I. Okay, so this fellow will be between 0 and 1 in this region. Okay, it'll start at 0 on the bounding plane and then it will slowly increase and it will go to 1. The moment it steps in, the moment it comes here, yi is still 1. But w transpose x plus b becomes what? Becomes negative, right? So this becomes -1. Right? So therefore, this becomes positive. So this gets added, as you said. So just to summarize, this region is 0 less than psi less than 1. This region is this is this region. This region will be what? This will be starting from 1. It will go till 2, and this will be 2 less than. Okay, less than. Okay, that is, if you want to be very precise, this will be all the other values of xi.
Sir?
Yeah.
Sir, when the rate point is beyond the separating margin, then it is the W transpose X plus B is becoming negative.
Correct.
And Y is still positive, no sir?
Y is still positive, yeah.
So it will, it will again turn to positive only. Okay, yes.
Right. So, yeah, that is correct. So we have to understand this as for the red points, this is the increasing direction of epsilon I. Epsilon I starts at 0 at this point, becomes 1 at the decision boundary, becomes 2 at the other bounding plane, and then it goes to infinity beyond. Okay, for the blue points, it will be just the reverse. It will be epsilon I will start from here as 0. Okay, and it will increase in this direction. Okay, so I hope that graph was clear.
Yes, sir, very clear.
Okay, so this psi I or ei is this. So what we can now do is we can now start formulating constraints. So notice that this ei is always non-negative. The other thing is I am just re-expressing this way. So yi into w transpose xi plus b will be greater than or equal to 1 minus ei.
How did you get that inequality, sir?
Good point. So see, there are two cases, right? One, when this red point is far away from the bounding plane, in which case this ei will be 0, right? In that case, we can't just okay, this kind of was a confusion to me also. It's tricky converting this from. Okay, can you stay with me till the optimization? I'll tell you.
Yeah, yes.
We'll argue this in a particular way, but this is a point of confusion. I agree. So just few more slides. Okay, when we get to that. So assume that you can do this, and that this is equivalent to this. We'll see why these two are equivalent. So the objective function, I'm just changing one thing. I am, in addition to maximizing the margin, or which is the same as minimizing this, I'm also penalizing the misclassification, not necessarily misclassifications, but the errors, right? So I'm penalizing those errors. So I have to minimize these errors as much as I can. At the same time, I need to maximize the margin. Okay, which turns out like this. So
Sorry, sir. That
C is just some constant. It's like the regularization that we saw in linear regression, which tells you how much I have to maximize the margin versus how much I have to penalize my errors, right? How much I have to, what is the trade-off between these two? Okay, so this will, let's take one example, then this will all be clear.
This C actually controls the bias variance trade-off.
I'm not sure if it controls the bias variance trade-off, but it controls the off. Yeah, in a sense, you could say that. So in linear regression, it does, right? The lambda for regularization kind of controls the bias variance trade-off, right? Maybe you can take it that way, but I'm not 100% sure of that.
So in some places we take C as the inverse of the regularization
Lambda.
rate.
Yeah, exactly. Yeah.
So is that same as this, or is this?
See, we can in a sense take it as 1 by C as lambda, because in linear regression, lambda into L2 ridge, right? So the lambda came here. So if you divide by lambda, you get C. In some sense, you can think about it that way. Right? So see, I know that it's not very convincing, but
so typically, if you have in this expression, once we increase C, essentially the margin decreases, so it is more looking like a hard SVM problem. If
correct.
you keep C small, then it looks like a soft SVM.
Exactly. Right.
And if we take large C, it will create overfitting. So I think it can be thought of like a regularization, right? It tries to find the balance between overfitting and outfitting. So that is a hyperparameter that we have to tune while we are playing with it. Yeah.
Right. So yeah, that is
large C will cause overfitting or underfitting? It will cause underfitting.
What is it?
Large C will cause underfitting, no?
No, overfitting here in this example.
okay. So I'm just trying to see, this is what we are going to do, right? So there are two terms in the objective. The first is maximizing the margin, right? So think about it this way. I can't draw it on both sides because it will take too much time. If I want to maximize the margin, it's the same as minimizing this, right? So if the first term predominates in this objective, what will happen? I will end up moving outside, right? Because my margin, that's the way my margin is going to increase.
Correct.
Okay, so that is when the first term predominates. Now, when the first term is high, what happens? Your errors start increasing, right? Because errors are defined as how far these red points are away from this line, right? So as you move this red line away and away, the errors are going to increase. Okay, so it's important to understand that these are in some sense not helping each other. If I increase the margin, then I also end up increasing the errors. Is this image clear for everyone?
Yeah.
Yes, sir.
Okay. On the other hand, if I decrease the margin, right, then my errors are also decreasing.
Yeah.
And that is what is controlled by the C. Okay, so that's the first thing we need to understand between what's the role played by norm W square by 2 and this term. Okay, now I'll just quickly come to address this question of why these two are equivalent. How do we address that? See, assume that, so the question is, why should this be an inequality, right? Why it's actually an equality?
So the points which are on the right hand side of should be equal to.
Okay, it's kind of tough to explain. How do I put it? So
Intuitively, yi wtx plus b should be less than or equal to 1 minus epsilon, right? So all points that are to the wrong side of the boundary, right, will be equal to 1 minus ei.
correct. All points that are on the wrong side of the boundary. So for example, the red point is on the wrong side of the boundary. I mean, wrong side in the sense, this is also wrong side, right? Not necessarily this.
Yeah, that's correct. I mean, anything that's to the left. In this case, red points are on the left side. Yeah, left side.
Yeah. So all such points should be, see, earlier what was it? It was, this should be greater than or equal to 1, right? Now what I'm saying is I'm giving some slack. I'm giving some slack and saying that it's okay, you don't need to be greater than or equal to 1. It's enough if you're greater than or equal to 1 minus the error. Okay, let me know if this is clearer. So earlier we wanted all points to be to the right of this line. Now for every point, what I'm saying is, it's okay, I'm giving you some slack and I'm calling the slack ei or e, and I'm saying that you don't need to be to the right of this line. It's okay, just it's enough if you're to the right of this line. So y into w transpose x plus b greater than, what is this distance from the bounding plane? It is 1 minus this is how I get the constraint. Is this okay now?
So the left-hand side is actually the distance of the point from the boundary, right?
This is the left hand side is the distance of the point from the boundary, right? This comes from our traditional way to compute the distance.
Yeah.
It comes
and
from
that we are saying is greater than or equal to 1 minus the error.
That is because of this being 1, right? So this distance is 1.
Okay, got it, sir.
Okay, so this is sometimes called the slack. Okay, why is it called the slack? Because you are not being strict in saying that all points should be greater than or equal to 1. Instead, you are giving some slack. You are allowing some slack, some error, and saying that all points should be greater than or equal to 1 minus the slack. Okay, so sometimes this is also called the slack variable, and slack is always greater than or equal to 0. Okay, so
but that slack we are not finding out. We are not minimizing. Is it a parameter or is it? Or by virtue of minimizing WB, we end up arriving at the right slack. Is it?
We are also enforcing this, right? So we are not just adding it as constraints, but we are introducing it in the objective. We want the slack to be as minimum as possible.
Right.
Okay, so this is why there is this trade-off, right? So if I see minimizing norm W is same as maximizing W, right? Which is the same as maximizing the margin. So if I maximize the margin, I will also end up increasing the slack, but I am supposed to be decreasing the slack.
Right.
Okay, but so if I try to, on the other hand, if I try to decrease the slack, then I'll end up making the margin smaller. So that's this trade-off, tug of war between these two terms in the object.
Yeah, that's right.
Okay, so see if you can do the same setup of, this is again a constraint optimization problem. This is a convex problem. You can convert it into the dual form, right? We are not going into that because that's not needed currently for our course. Okay, so this is the formulation of the soft margin SVM. Okay, there is a slight confusion here. We have given this gradient descent solution as the soft margin implementation. I am not quite convinced that that is actually right. Okay, so I'll tell you why. So one small update here for the next OPP and in general, right? We will typically only deal with soft SVM, right? Till soft SVM, we'll have it. Kernel SVM, it's good to know what kernels are. You can read it up, but this kernel SVM implementation will not take it up.
So, but gradient descent solutions aren't feasible in SVMs or something else is the problem.
Yeah, that's what. Yeah, I'll come to that. So that is what I want to discuss in the next 10 minutes or so. See, this is the objective, right? The soft margin objective. Now, what we can do is, this is where the whole hinge loss and all that comes in. We can rewrite these two constraints in this form. Do you all agree that we can do this? For points that lie beyond the margin, this error is going to be 0. For all other points, the error is going to be this, right?
Yep.
Okay, so what I do is I just substitute that xi I into this objective function and make it an unconstrained optimization problem. Okay, so this is unconstrained. This is also convex. And we can use gradient descent. But there's one problem. Do you all see what that problem is?
Max of.
Is it differentiable everywhere?
Right. Yeah. So those we can fix, right? So those we can just take these gradients piecewise, right? And assume that we can do gradient descent, but what other problems do you foresee?
What about us forcing the slack to be all positive? Okay, that is there.
That is there, right? So see, the biggest problem is where are the support vectors, right? If I solve this problem, I am going to directly get W, right? I'm going to get W. Where are support vectors now? So why should this be called support vector machines then? In our hard margin, we saw that we ended up with some support vectors and we justified calling that algorithm SVMs in that sense. But if I'm going to solve this problem, I'm going to get some W and B. So why should I even call this support vector machines? What's so special?
So, but after finding the optimal weights, can't we just calculate the support vectors somehow?
That is the problem, right? See, the support vectors are not just those points which lie on the bounding planes in the case of soft SVM, right? So you can please do check out this Bishop's PRML. So for the soft SVM case, you could also have points which lie inside the margin acting as support vectors.
Yeah.
Right. So I am not totally convinced that this is the soft SVM implementation, whatever we have given. Kind of not convinced, but anyway, we'll stick to this as I'll just call it approximate solution to SVMs until we can clarify this part. But yeah. Anyway, so there are few things to be seen here. This is treated as some kind of a loss function, right? I hope you all see that. These are the errors, right? So C is, as I said, some kind of a regularization term that controls the trade-off. Right? How much I can tolerate this violations of the margin. Okay. So I think this we also discussed. This should remind you of regularized linear regression, where the lambda was here for linear regression. Here we have C instead of lambda. Okay. And these are two cases. Can someone tell me what will happen in these two cases when C is a very small number? What do you think will happen if you minimize this?
It becomes like a hard margin problem.
Does it become like a hard margin or?
Actually, opposite. For large C, you are doing hard. Basically, in a hard case, you do not tolerate any slack.
Right. So when C is very small, what is going to happen? You are basically saying it's okay. You can, I can tolerate a lot of slack, right? Even if you make a lot of errors, I'm fine with it. So I am actually encouraging my solver to increase the margin as much as it can. Right? That is what is happening. Does everyone see that? If C is very small,
whatever error is being computed, it's being we're calculating, we're multiplying a fraction of it. It's just taking a very small error.
Yeah. So the whatever error we are computing, you're right. We are multiplying it by a very small number. So my slack doesn't matter much in this case. My margin, I am like given a free rein over my margin, so I can make it really large. Right. So this is what happens in C much less than 1, and C becomes large. What will happen?
It's more like a hard margin.
Right. It's more like a hard margin, right? I cannot tolerate slack. I cannot tolerate slack because this term will become very high, right? And C is a very big number. So I will immediately make this as small as possible, right? So which is like getting a smaller margin, but it resembles the hard margin case where most of the points I try to classify correctly.
So, sir, we are actually like finding a solution to that trade-off.
We are not solution to the trade-off, because we are just discussing what happens if you choose different values for the trade-off parameter.
So if C is very small, that means I am kind of neglecting what we just learned, that error part.
Yeah. So neglecting, as in you're saying that it's okay if I
Yeah,
make a lot of errors.
it's okay if I make a lot of errors, and so now it is saying that I can increase the boundary, boundary margin.
Correct. You are free to increase the boundary margin because that will minimize this term a lot. So you're happy doing that.
Yeah, so I am free to increase the boundary margin. Now, so this is for when I am decreasing C. So now, in order to uh, do it correctly, I need to find
a good value of C.
Yeah, good value of C such that both of these thing is maintained.
Correct. Yeah, you are right. So for that, what we'll do is we will do some kind of, say, a line search or grid search. If you are doing MLP, then we will look at we'll take up different values of C in an interval, say powers of 10, right? 0.1, 1, 10, 100, and see and look at the validation loss. In the data set, we'll compute the validation loss and see for which value of C I am getting the least loss. I will fix that C, right? And I'll say that this is the best for my data set.
Yeah. So it is part of hyperparameter tuning. It's a hyperparameter that needs to be tuned.
Right. Okay, so this is called the hinge loss. So 1 minus this, right? So I'm just taking 1 out of the n sums, right? And this thing is the hinge loss. So if you plot it, I'm just calling this whole thing Z. If you plot it against Z, it will look something like this, right? For Z greater than 1, it will be 0. For Z less than 1, it will be positive, right? It will be just 1 minus Z. Okay, so the only thing that remains if you want to do gradient descent is find the gradients. So for f of z, this is very simple. It's 0 when z is greater than or equal to 1 and minus 1 otherwise. If you were to do it for this objective, that with the W transpose X plus B part, then this is how it will look. Okay, is that fine? So this you just substitute into your gradient descent and it should hopefully work.
I don't know what was happening with my code.
Right. Okay. So it's still not.
It's been 2 days. I'm trying to debug.
Okay, we'll look into it. Yeah. So probably in the next session we'll take it up. So
Sure.
yeah, any questions so far? Okay, so that's all I had for SVMs. Right, as I said, from our core standpoint, please do this hard margin, soft margin, and the implementation using gradient descent. Kernels, you need to know what kernels are, but more than that, we don't expect you to know.
So won't kernels be important for deep learning?
Sorry?
Won't kernels be important for deep learning?
Not really. I'm not sure if it is that important because I don't think so.
So can you tell me what is the difference between suppose in case logistic regression, we sometimes what we perform polynomial transformation of the features, right? And here there is a kernel called polynomial kernel. So what's the difference between that?
See, the difference is that in polynomial transformation, we explicitly do the transformation, right? We transform it into some, say, higher dimensional space explicitly in the sense that you do x1, x1 square, x1, x2, x1, x2, x3, like this, right? But a kernel, what it does is it does this implicitly. So there is a kernel function of for the polynomial kernel where it's going to give you the result of the dot product in that space, right, in that transform space, but without having to transform it explicitly. Okay, I mean, I don't do this I don't first construct x1 square, x1 x2 so on, and then take the dot product. All this I don't do for a kernel. I just plug in x1 and x2 into my kernel function and it returns the dot product in the transform space. Okay, so I bypass that process.
So basically, if our data is linearly unseparable, then we apply the kernel trick, so the data can go into the higher dimension where it can be linearly separable. So we solve the problem there and come back. That's the whole reason why.
That's the whole thing. Yeah.
And then what is the case with polynomial transformation? There also, we actually bend the decision boundaries.
Yeah, so that is separable, but not linearly separable, right? So there are basically three conditions: linearly separable, non-linearly separable, and then linearly unseparable, right? So these are three different situations. So if it is non-linear separable, but not like in a straight line, you need a curve maybe. There you would do some kind of transformation so that your decision boundary is not like a line, but like a curve. I don't know if I'm making sense.
Yeah. Right. So anything else that we need to discuss for SVMs, or are we done with SVMs?
So implementation of kernel, we don't no need to give much importance right now.
Yeah. See, if you look at the questions, right? There is one graded question on Hinge Loss. That is okay. There is one on this is what fit Hinge Loss again. There is no kernel here, so
all questions are more or less the same.
Yeah, so don't. I mean, if I say don't study it, I will be doing something wrong. So, from the exam point of view, we won't test you on kernel SVMs implementation. Okay, because we need to first understand it properly before we expect you to do it. So, see, typically in all solvers, if you look at all SVM solvers, they try to solve the dual problem. Okay, there are some, even sklearn. If you look at sklearn uses two libraries called libsvm and liblinear. I think there are like two different libraries. So these libraries use some kind of solution where they try to optimize the dual, right? Whereas if you notice what we have here, we are applying gradient descent to what? This is gradient descent on the primal problem, right? So I'm not convinced if this is kind of the right thing that we are doing, but for now it's okay.
So one more thing, in the graded question, there is the last two questions are like what is the kernel? It's not the programming; it's a graded assignment. Yeah, the last two questions. What is how do you find the kernel? So it's that the dot product, or how do you find it?
See, this is
it's asking a suitable kernel, use a suitable kernel. So what does that mean?
Okay, so see, this is the transformation, right?
Yeah.
Now, what kernel should you use so that the dot product, I mean the kernel's output and the dot product in this transform space turn out to be the same? Did you get the part?
No, sir.
So see, do you understand what a kernel actually does?
No.
Okay, so yeah, so that part we didn't explain at all. So I don't blame you. So there is Okay, there is a chapter on kernels, which is where these things have been taken from. The chapter is 6, page 291. See, this is the margin. Okay, so that whole thing is not the margin, but anyway, it's fine. Where is the kernel? So for this problem, you use this information. If these are the kernels, which of the following will also be a kernel? Again, this we didn't teach you in the slides. So for that, you have to refer to this. How to get kernels. So this is on page 296. But to understand the idea of what a kernel is, okay, let's take this. See, this is, I think this is what this question is asking. But anyway, since we haven't taught this explicitly, I think it's good to, okay, you have two vectors. Okay, you have two vectors. What are they? Two-dimensional vectors, right? X1 and X2. So X is X1 comma X2 and Z is Z1 comma Z2. So the idea of a kernel is, what do they call the kernel? K of X comma Z, right? The idea of a kernel is transform both these vectors to some higher dimensional space. Let's call that transformation phi of X, right? And that, so kernel is equivalent to the two things. First step, like implicitly transform X and Z to some higher dimensional space. Second step, take their dot product. Third step, return this as output. So if you treat kernel as a function in Python, this is what it's going to do, right? So step 0 will be accept two vectors as input, transform X and Z to some higher dimensional space, take the dot product in that transform space, and the final step is return this as output. That is what your kernel is. Okay.
So
now,
the second step is given as the function over there.
The second step is the the second step is what is given here. So see, the idea of kernel is one and two are going to be kind of hidden steps, right? So that's why I said implicitly, meaning you don't even need to know what that space is. So the kernel essentially is just this: accept two vectors are input, return some scalar value as output. Okay, but you know what it's doing internally is this: it is transforming them into some higher dimensional space, taking the dot product. So see what I'm doing here. We are doing step 2 now, which is transforming X into phi of X, transforming Z into phi of Z. Okay, and then I'm taking that dot product. Okay, so in this example, what they have done is they have used this particular transformation. So this is one kind of kernel that you can get. So phi of X is, what is that? X1 square root 2 X1 X2 and then X2 square, right? So this is some kind of polynomial transformation, right? I hope you can see that.
Yes, sir.
This is a degree 2 polynomial transformation, but with some special coefficients. Okay, so this will be phi of X. Now I can do the same transformation for phi of Z. So this will be Z1, Z1, Z1. Now if I do phi of x transpose phi of z, what do I get? I get
x1 square, z1 square.
x1 square, z1 square,
2 x1,
x1, x2,
z1, z2,
plus x2 square,
z.
z2 square, right? So this is what I get. Now this is nothing but x1 z1 plus x2 z2, the whole square. Is that right? Okay, so what I am suggesting as the kernel is this function. See, this is internally, this is nothing but x transpose z the whole square. So now compare it with the 4 steps that I wrote. Sorry. So this is what I'm going to do. Accept 2 vectors as input. This will be step 0. Return some scalar as output. This will be step 3. Steps 1 and 2 are what I have done here. Okay, so this is what a kernel is basically.
Okay, sir.
Okay, so so this question is essentially asking you to do that. So it's giving you this transformation that is internally happening. Yeah, but I still kind of agree that this is. So were you taught any of this in the lectures? What is this? Which is a suitable kernel?
Actually, from lecture, I didn't understand anything.
Okay, I think this is not, maybe we didn't cover it. So
The part which you explained just now, that was explained in the lecture, sir. This thing.
this is explained, is it?
This thing was explained, but suitable kernel and all that, that was not explained.
Okay, for suitable kernel, please refer to valid kernels. So see, this is basically, see, we are asking what, see, these are 2 kernels, then which of the following will be a kernel? Okay, so this image is not there in the slides, right?
This one, sir, this k of x comma x. No, sir, this was not there.
Okay, then you have to refer to this. We have to add this to the slides. So you have to, only if you know this, can you answer this question? Because otherwise you don't know. I mean, this, see, even PRML has not given proofs for this. So these are.
So, sir, the end product that we got in the proof, yeah, this one, x transpose z whole square. This end product is my kernel, no, sir?
That is your kernel, yeah. So all this is just to prove that this is a valid kernel. So steps 2 and 3 are just to prove the validity of the kernel, right? So no one will give you all this. They will only give you that the kernel is k of x comma z is x transpose z whole square, right? So that is all they'll give you. Okay, so anything else?
And is it possible to share today's that slides?
Yeah, so slides are here. So you have to just go to this particular slide. So this particular web page.
I'm getting a 404 error for the link that you put in the chat.
So did you access that exact link? Because unless you get that link,
Can you paste it again? I didn't get that.
Yes, sir, it opens now.
Okay, so this exact thing will open. So one to 7 will only open. So you have to do starting from 1 to 7. Okay, then I think that's all. That's all we have. All the best for your OPPE.
Thank you so much, sir. I've covered a lot of ground, so I think I'll certainly need a review of the videos that you've put out.
Right, right. Yeah.
This will help in OPE 2 actually.
True.
Sir, will you be there in week 9 also, sir?
I will be there in week 11 and 12 from now. So 9 will be Nitin, 10 will also be Nitin, and then yeah.
Thank you, sir.
Yeah.
Thank you very much, sir. Very helpful, sir.
Thank you
very
so
much.
much.
Thank you.
Yeah.